All right, we're now going to talk about assignment 5. Now, let's refresh some things. Next class, if we were doing true-false, next class equal to p time, we would have to say nobody knows, so that's open. If we want to ask whether p equals np, nobody knows, so that's open. If we want to ask whether np equals p space, nobody knows whether that's open. Well, we know this is a subset of that, which is a subset of that, which is a subclass of that. However, going all the way from this to this is NC equal to P space, and the answer to that question is known to be false. So NC and P space are definitely different. All right, I'm now talking about problem 1, which is the true-false. For A, regular language membership problem is known to be a mixed class. That's true. Why? Well, it's actually fairly easy to prove, and perhaps it'll be on the next homework. Now, the context-free membership problem is known to be a mixed class. That's also true, but the proof is very hard, and it was only recently published. However, it's known to be true. You can find it out there. Actually, I'm not sure you can find it, because I could not find it on the internet. I had to send email to an expert to get an answer. The set of all recursively enumerable languages is countable. That's true, because every recursively enumerable language is accepted by a Turing machine, and there are only countably many Turing machines. Every context-sensitive language is in p-space. Now that's actually true, and it's on the internet. You can go look it up. Now here it says NC equals p-space. Well, that I just did in the previous frame, previous slide, and that one is known to be false. All right, now let's look at the problem F. Suppose that someone solves the integer factoring problem in polynomial time. In that case, what would the consequences be? The consequence would be that RSA encryption would no longer be secure, because it's a one-way code, meaning that it should be easy to encrypt something if you have the key, and without the key, it's difficult, it's extremely hard to decrypt it. Actually, you don't need the key to encrypt it, and you do need the key to decrypt it. In that sense, it's a trapdoor encryption method. Now, if factoring were easy, then, or in polynomial time, then if you knew the key to it, if you could encrypt, you could also decrypt in polynomial time. And that means that RSA coding would be insecure. However, that would not be a proof that there was no trapdoor, secure trapdoor encryption method. And so in that sense, the answer to F should be false. On the other hand, we can interpret it a different way. If P equals NP, then polynomial time is the same as NP time, which means that if you could encrypt in polynomial time, you could also decrypt in polynomial time. In which case, since we don't know whether P equals NP, we would have to say that the answer to this question is open. Now, because of this ambiguity in the meaning of the question, I will accept either O or F as the correct answer to this problem. All right, now the last problem is that the decidability problem is decidable. That doesn't seem very likely true. It's actually false, and I'm not going to explain it right now.
1.
Now, in this problem, I'm asking you to find a polynomial time reduction of the subset sum problem to the partition problem. The subset sum problem consists of all tuples where the first number is something called k, let's call it k, and there's a sequence of other numbers, and there is some subset of the x's whose total equals k. In other words, the sum of some subset of a bunch of objects of these weights. Now, the partition problem is, if you have a bunch of objects of various weights, is it possible to find a subset whose total is exactly half of that total? It's pretty clear the partition problem is a special case of the subset sum problem. So there's a trivial reduction of partition to subset sum. But I asked you to find a reduction of subset sum to partition, which is the opposite, which is somewhat harder.
1.
Now we're going to show a reduction here. The subsets of the subset sum problem to the partition problem. We could take an instance of the subset sum problem, which would be a number k followed by a bunch of other numbers, a sequence of other numbers. Now the way it's usually phrased is both you have an object of weights, all these objects of weights 1 through xn, 1 through xn, and then a total, and you're trying to find a subset of those objects whose weight is the total. And an example would be if you have a bunch of coins of various values, can you find a subset of coins whose total value is, shall we say, 50 cents? That would be the subset sum problem. And on the other hand, the partition problem in terms of coins would be, if you have a set of coins, can you divide them into two piles that have equal value? And the answer to that is either yes or no. So both of those are decision problems. Now the reduction, here's an instance of the subset sum problem, an arbitrary instance. Now this value is k, and the sum of these values, we'll call it s for sum. And now what we're going to do is to start with these objects here and create two more objects. One has weight k plus 1 and the other has weight s minus k plus 1. And you notice that when I add these up, these objects total s, there's k plus 1, there's s minus k plus 1. You do your algebra and you can see right away that the total is 2s plus 2. Now, if you want to divide these objects up into two equal valued sets, both sets will have weight s plus 1. All right, now let's take an instance of this is an illustrative instance. Here's an instance of the subset sum problem. We're given k is 12, and we're given a sequence of numbers which adds up to 27. Now, we take the same objects here, 518, 543. We create two new objects. This is k plus 1, which is 13, and at k minus s plus 1, 27 minus 12 plus 1 is, of course, 16. Now, we want to show that if there's a subset here that adds up to 12, then there's a subset here that adds up to 28. S plus 1, which is 28. Now, what we would have to do is take a subset of these that adds up to 12 and throw in 16, and we get 28. And this works in general. This is just an instance. All right, on the other hand, how would we go the other direction? If we can find a subset that's half of them, we have two sets whose total is s plus 1, which is half of 2s plus 2. And we know that neither of the two sets can contain both of the last two elements because their sum is s plus 2, which is larger than possible. It's larger than s plus 1. So therefore, one of the two sets contains the last element, which is s minus k plus 1. That means that the remaining elements over here must add up to k, because this one is s minus k plus 1, so what's left over has to be k, and therefore that gives us the subset here that adds up to k. Alright, we're now doing problem 4. We're going to say that a language is, well, recall the definition, it's in the class co-RE. If given any string which is not a member of L, there is a proof that the string is not a member of L. Now what that means is you put in any string over the alphabet, there's this Turing machine here which will tell you no if and only if the answer is no, which is the opposite of RE. And so if the string W is a member of L, the machine doesn't have to ever answer you. Now we're going to find a proof of what? Given two context-free grammars, we're going to define L to be all the set of all pairs here, so that the languages generated by the two grammars are the same. All right, now we want to prove that if a string is not a member of L, we can prove it. We'll start by saying, well, without loss of generality, they are both over the same alphabet. And then we can visit sigma star in canonical order. So we're going to draw an infinite for loop for all W member of sigma star in canonical order. All right, now we're generating one at a time all these strings. Now we can assume that sigma is the binary alphabet, and so that means that this would be all binary strings. We're looking at them one at a time, starting with the empty string, and then 0, and then 1, and then 0, 0, and so forth. Now, what we can do is, for each of these strings, we can use the CYK algorithm to decide whether W is a member of this, and we can also use the CYK algorithm to decide whether W is a member of this language. So now we say, well, if W is a member of LG1 and not a member of LG2, and we can decide both of those two questions, then we halt. Because we now have a proof that LG1 is not equal to LG2, because there's a string that's in one but not the other. On the other hand, of course, if you do it the other way, if W is a member of LG2 and W is not a member of LG1, then of course, again, they're different, they're not equivalent, so we halt again. Now, if neither of those is true, our infinite loop just keeps running. Now, if the languages are actually the same, this program never halts. So it doesn't give you the answer. And so what happens is, if we have our program P, and we input the string G1, G2, we will get no. We're going to get this answer if the string, if this is not a member of the language. Not a member of that. So we can take that halt as a no answer to the question of whether they're equivalent. If the correct answer is yes, we'll never get it. And therefore this language is in the class co-RE by definition. We're now going to talk about problem 5. Now, we don't know whether any two of these things are equal, but that's why I use the phrase known to be. And we look at these different languages, or actually problems here, and we decide which of the 5 classes, which of the 6 possibilities is the correct answer for that. Now the way I have it is there's one of each. So the 6 questions, use each of the 6 answers. Although I didn't say that that would be true, that is true. All right, now I'm going to now explain this. Now we're doing the last problem here. I've given you 6 classes of languages, and in each case I say P but not NC. Now of course we don't know if NC equals P. So what I mean here is we don't know that it's NC, and here that it's not NP complete. So that's category 2. And again, since P is, we don't know whether it's NP, this is not actually the definition. It's the definition given in the homework is it's polynomial but not known to be an NC and not known to be NP complete. All right, with that, that's the way I'm writing it from here on. NP but not P, but also not NP complete. Here's number 4, NP complete. Number 5, polynomial space, but not in the class NP. And number 6 is not in polynomial space. So these sort of a progression from easiest to hardest. All right, now I'm giving you each of these problems, and the question is, what is known about these problems in terms of this category? Now, I have told you the Boolean circuit problem is P complete. It's an X class problem, and if the Boolean circuit problem is in the class NC, then NC equals P. So this is the hardest kind of problem. Well, in P, I won't say it's the hardest problem in P. It's the hardest problem subject to the concept of NC. So this one is in 2. All right, now the rush hour problem, it's a game you can buy in a toy store. And you have this rectangle with a bunch of cars, different trucks and cars of different lengths that can slide horizontally or vertically, and you have to somehow slide them all around so that the red car goes out the opening. And the question is, given a configuration, is it possible to get the red car out the opening? Well, that problem is definitely in the class P space. That's known. It's actually P space complete, I believe. But it is not known to be in the class NP. In principle, the answer could be yes, but it could be that the proof that the answer is yes has exponential length. So that, for all we know, for a given problem, the answer could be yes, but the answer could be yes, but the solution, and how to get the car out, could be enormously long, much more than polynomial. So rush hour is in the category 5. Now, factoring, by that I mean integer factoring with, let's say, binary numerals, or it could be decimal numerals. Now, the reason I said binary numerals in the homework is that if you use unary numerals, factoring is in the polynomial class. But people don't usually use unary numerals in practical ways. So this one is an example of a problem that is in the class NP. Now, it's not known to be polynomial. If it were, then RSA coding is insecure. But it's also not known to be NP complete. That problem is also open. So that's in category 3. Now the Boolean satisfiability problem is NP complete, so that's a 4. Context-free membership is how did that one get in here? I don't think that was the correct question. The context-free grammar membership problem is known to be, oh, I'm sorry. That's known to be in the class NC. That was a question that was a previous question. Generalized chess means Well, chess is a finite game, so you have to generalize it to make it into a class where you can answer these questions. And that means take all possible chess games or larger chess games, bigger boards, more different kinds of pieces. And that would include checkers, for example. And take any game of that type and ask the question, given this configuration, can the first... It's known to be exponentially complete, I believe. So therefore, that's in class 6.